the elastic curve method. Okay. So again, I will explain to you what this is. Okay. All I can tell you is this. Okay. We just need to integrate 2 more times. That's all. Okay. We just need to integrate 2 more times. So the elastic curve method, okay, is used to calculate the slope and deflection of the beam. Okay, so that's the purpose. So the elastic curve equation, again, I'm not going to derive this. Okay, the elastic curve equation is equal to EI. So EI is equal to which is d squared y over dx squared is equal to moment as a function of x. So this expression over here, again, I'm not going to derive this. Okay, it will take me another half an hour. I'd rather go into application for you for this and analyze and how to use this equation. Okay, and what are the operating boundaries and when to use this equation. And this is, again, really powerful technique together with the integration method to solve statically indeterminate structure. Okay, so what we have down here, this is what we call the elastic curve equation. Okay, where E is the Young's modulus, and I is the second moment of area. Okay. So now, if we have a beam now, okay, so this is our beam, and our beam, one end is a pin, the other end is on a roller, and we have a force P, okay, acting somewhere around here, right? So I'm going to superimpose my axis. So this is y. Y over here dictates deflection. Okay. And then this axis over here, this is x. That is why we have our expression d squared y and dx squared. Y is the deflection, x is any position along the what? Along the beam. Okay. So if we were to sketch the deflection of this beam, okay, again, this is a sketch. This is how it's going to look like. Okay, we're going to sketch. Okay, so this is our axis. Hey, G. X, right? And this is our Y. I'm drawing below because we know that it's going to be deflecting downwards, okay? So the deflection of the beam will look like this, okay? So this is how the deflection look like. Okay, this is how the deflection will look like, okay? So from here, let's say we pick a point, okay? We pick a point, a certain point that we pick, and this point is here, okay? We pick this point here, okay? So we know the distance from here to here right, up to our point over here, right? This is our distance x, okay? And at this distance x, we know that we have a deflection. Okay? So deflection is y. And the thing is, you ask me, Eugene, what is the slope? Okay, so if you were to draw a line tangent to the point, so this is the line tangent to the point. Okay, and you were to sketch a horizontal line over here, this is your theta. And theta is known as the slope. And what we realize over here is where the slope, like at this point over here, is where theta is equal to 0, okay? Deflection is maximum. Okay? So let me write out the solution procedure before you go for a break to smoke something heavy. Okay, so when you look at this, you really need a smoke break, I'll tell you. Okay, so if we were to write down the solution procedure, this is how it goes. Okay, if we were to look at our solution procedure, we have dv over dx is equal to minus omega as a function of x. Yes or no? So this is what we know already. This is what we learned before, right? Then we integrate once. We have v as a function of x is equal to minus omega x dx plus by c1. Okay. Then after that, we integrate again.
Does E and I remain constant in the equation above?
Yes, yes. So this will be equal, this is also equal to dm by dx, right? We've done this. So now m as a function of x now. So you integrate twice. Minus omega as a function of x once, twice. Now this becomes c1x plus by what? c2. Okay. Then over here you let it equal to dei d squared y over what? dx squared. So when you do this step, this is known as applying. You apply the elastic curve method. Because the elastic curve method, right? Initially when we write what? EI d squared y over dx squared is equal to m as a function of x. Okay, so from here, you integrate number 3. So it will be equal to EI dy by dx. Now this is equal to EI theta, right? dy by dx is equal to theta. So this is the third time. Minus omega as a function of x. 1, 2, 3 plus by c1x squared plus by c2x plus by c3. All right, and then the fourth time you integrate. So this will be equal to EI y is equal to integrate 1, 2, 3, 4 minus omega as a function of x. 1, 2, 3, 4 plus by c1. Hey, I forget my 2 down here. c1x cubed over 6 plus by c2x squared over 2 plus by c3x plus by what? c4.
Eugene,
So
that should be 3.
where?
The C1 x3 x cubed over 6.
Yeah, it's 3, right?
Yeah.
Yeah.
It's n
This one.
plus 1. on the bottom.
It's okay. It's still correct, right?
No, the C1 divided by 6.
Yeah, divide by,
It's correct.
right?
It's 3 times 2.
Right? This is correct, right?
Yep.
Isn't it the formula n plus 1 on the denominator?
There's
Is
a 2 there.
It's correct, okay? So now, Colin, wait, you go and do the integration, okay? You've done math earlier than me, so you go and do the... Now the thing is this. How many constants we have? Anyone? We have how many? 4 what? Constants. So when you have 4 constants, you need how many boundary condition?
Eugene,
Yes.
the cubed is n plus 1, not n times it. So it should be cx cubed divided by 3.
No, there's a squared over here. There's a 2 at the bottom.
Because
Oh, yeah.
because it's 2 times 3.
Okay.
Thank you.
Yeah.
Right? So now, right, you have 4 constants. You need how many boundary condition? 4 boundary condition. Okay. So again, I'm telling you, it is not that difficult. Again, I express myself, it's not that difficult. Go for a break. Come back. We come back at 8:20. Sorry, yeah, 8:20. We come back, we carry on. Okay. Thank you.
Cool.